In this video, we'll conclude Unit 6 by talking about design spectra. The key question is, how do we design for future earthquakes? So far, we've assumed that we know the ground acceleration u_g, but looking back through historical records, we see that every earthquake is quite different. For example, if we look at the Koina earthquake, which we mentioned was very high frequency, short period, we might expect to see a pseudo acceleration spectrum that is high for low periods. Comparing that to Mexico City, we might expect a pseudo acceleration spectrum that is higher at higher periods. In other words, it excites large responses out of structures with high natural periods. Each of these response spectra are going to be influenced by a large list of factors, including the local soil conditions at the site, the distance from the fault mechanism or the earthquake mechanics, the magnitude of the earthquake, and we could keep going. So what we really desire is some sort of representative spectrum that could cover a wide range of earthquakes for a particular location with some sort of level of acceptable risk. So let's look at the El Centro response spectrum once again and try to extract some general characteristics of a typical response spectrum. In this case, we've rescaled each axis in order to normalize by the ground motion. So the displacement response spectrum axis is normalized by the maximum ground displacement. The pseudo vibration axis is normalized by the peak ground velocity, and the pseudo acceleration is normalized by the peak ground acceleration. This allows us to plot dotted lines for the unity value of each of these spectra. So what we notice is that as we move to the left side of the spectrum, in other words, low period, all the spectra seem to converge to the dotted line corresponding to normalized acceleration of 1. This means that the pseudo acceleration matches the ground acceleration. This is typical for an extremely rigid or stiff system. In other words, the mass and the ground move together. If we move over to the right side, we notice that the same thing happens, but with the unity line for displacement. This is typical of an extremely flexible system. In this case, the ground moves, but the mass stays completely still. Elsewhere, the spectrum is amplified. And this amplification is going to depend only on damping, since the influence of the ground motion and site conditions have been removed by normalizing the axes by the ground motion. So given these three characteristics, we can now create an idealized spectrum. We start by dividing the spectrum into three spectral regions, which you see at the top. An acceleration sensitive region to the left, a displacement sensitive region to the right, and a velocity sensitive region in the middle. In the acceleration sensitive region, it is possible to define the pseudo acceleration response simply as a scaled version of the ground acceleration. In the displacement sensitive region, it is possible to define the displacement response as a scaled version of the ground displacement. And in the velocity sensitive region, it is possible to define the pseudo velocity response as simply a scaled version of the ground velocity. Given these three regions, we can now idealize the spectrum as a set of interconnected lines running through points A, B, C, D, E, and F. The line running through point A is going to have a normalized pseudo-acceleration value of 1, whereas the line running through BC will be amplified from 1 by a factor alpha A. On the displacement sensitive region, the line running through F is going to have a normalized displacement value of 1, and the line running through D and E will be amplified by a factor alpha D. And in the velocity sensitive region, the line CD will be amplified from a normalized velocity of 1 by a factor alpha V. Now, just as the true spectrum will amplify as damping goes down, so will these factors. The values of alpha that we choose are going to be dictated by the damping of the system, but also by the amount of risks that we're willing to tolerate. In order to understand how to amplify our spectrum appropriately, we need to look at not just one ground motion, but an ensemble or set of ground motions. And this is where the idea of mean spectrum comes in. So taking a set of historical ground motions, we can generate a representative spectrum for a particular site. This mean spectrum is generated by averaging each period ordinate individually. So each point in the spectrum is an average of multiple spectra. Therefore, for each point, we can also generate a probability distribution, which may vary depending on the period as well. So in this way, we can generate not only a mean spectrum, but also a mean plus 1 standard deviation spectrum. The mean spectrum will give us a 50% probability of non-exceedance. The mean plus 1 standard deviation spectrum will give us a probability of 84.1 non-exceedance. Notice how the mean spectrum fits much more closely to our idealized spectrum. The only thing left to do is to define the exact positions of A, B, C, D, E, and F. It is recommended that the period values corresponding to A, B, E, and F be fixed at the values seen here. However, the values for TC and TD will depend on how much we choose to amplify our spectrum. So those will be calculated during the design spectrum creation process. So putting everything together, let's look at how to create a design spectrum from scratch. Step 1 will be to obtain values for peak acceleration, peak velocity, and peak displacement. And to plot these on their spectrum as so. Step 2 is to pick a desired percentile and damping value and obtain the appropriate alpha values. Let's say we will go with the 1 sigma spectrum and 2% damping. And that way we will pick our values for alpha A, V, and D. Step 3 involves amplifying our respective segments of the spectrum. So we will amplify the line BC by alpha A, the line CD by alpha V, and the line DE by alpha D. Note that in this case, the corresponding spectrum values for B and D are fixed. Once we amplify, the intersection of BC and CD will give us the corresponding value for TC, and the intersection of CD and DE will give us the corresponding value for TD. Step 4 is to draw the lines through A and F. Here, these are simply lines corresponding to unity values for A and D respectively. And finally, our last step is to draw lines AB and EF. These can be defined by a simple log linear relationship. So in the case of AB, we can state that the log of A, the pseudo-acceleration, is equal to some slope value A times the natural log of the natural period times some y-intersect value B. Alternatively, we can express that as A is equal to e to the b times tn to the value a. Little a can be defined simply as the slope of that line. So using logarithmic identities, this can be simplified to this quantity, where a sub a is the value of the pseudo-acceleration at A, and a sub b is the value of the pseudo-acceleration at B. And finally, B can be obtained from the log of AB minus A times the log of TB. Okay, so let's look at how to apply that to a concrete example. Let's say we are creating a design spectrum for a specific site, and we've been given values for peak ground acceleration, peak ground velocity, and peak ground displacement. Now these could come either from historical ground motion records or just from engineering experience. But either way, these are our nominal values for u double dot g naught, u dot g naught, and ug naught. We're also asked to do this for systems with 5% damping and construct the 84.1th percentile design spectrum. These are going to dictate our choice of alpha. And finally, we'd like to determine the equations for the pseudo-acceleration design spectrum. In other words, A as a function of Tn. So we have the values for step 1 right here. So let's go ahead and plot those. We're going to find the line for 1g and draw that out. The line for 48 in the pseudo velocity, and the line for 36 in displacement. That is our step 1. For step 2, we need to find our alpha values. For that, we'll have to go back to our table. In this case, we are still in this column, but considering values for 5%, so our respective values will be 271, 230, and 201. Step 3 is to amplify the ground motion spectrum by the alpha values. First, we'll find our period corresponding to B, which is 1/8 seconds, or 0.125 seconds. Project that line up, and then we amplify our ground acceleration UG naught double dot by 2.71. Since that is 1g, that'll give us 2.71 g's. We'll do the same with UG naught dot. If we multiply 48 times 2.3, we get around 110, which is slightly above our graph. So we'll just simply draw it here. Naturally, we need to extend this line just slightly. And then finally, for displacement, we need to amplify by 2.01 times 36. That gives us 72.36. Here we also need to find the corresponding value for TE, which is 10 seconds. And so now we have our points E, D, C, and B defined. At this point, we can find the remaining period values TC and TD. TC is roughly 0.6. TD is roughly 4.5. Step 4 consists of drawing the unity lines. So for the first one, we'll start all the way on the left and go up to TA, which is at a period of 1/33. That is roughly 0.03. And on the other side, our F is at 33 seconds. And so that's our line there. And that's our A. So now we have all our points defined. The last remaining step, step 5, is to connect these lines. And so our final spectrum looks something like this. And this can be used just like an earthquake response spectrum. Now the last thing to do will be to extract equations for the pseudo acceleration spectrum A. Now this will be a piecewise function for each of the line segments. You can see the solution here. I will just point out a few things. For Tn less than Ta, the acceleration will be constant. Same thing for between Tb and Tc. For Tc and Td, the velocity is constant, not the acceleration, but we can easily convert to acceleration using the relationship between each of the spectra. So in this case, we just multiply by 2 pi over Tn, or the natural frequency omega n. We also need to make sure to divide by g to get into the right units. Same thing applies for Td to Tae, except in this case we're using a constant displacement and multiplying by 2 pi over Tn squared. Always making sure to divide by g. Same thing for Tn greater than Tf. The trickiest ones are those connecting line segments. Again, I am just using a linear log relationship here, deriving the slope and the y-intercept in the log domain, and then simply converting that to the linear domain. Similarly for Te to Tf.